With our compound interest formula here, one thing we may be asked to solve for might be the time, as in how much time something takes to do something. And in order to solve for time, that's an exponent. And remember, to solve for an exponent, we need a little mathematical thing called a logarithm to be able to do that. So example 6 is just a refresher on something we've already covered once before. And in this case, it says 3 to the power of x equals 20. So what we're saying is 3 to some power equals 20. We have an idea of what that may be because we know 3 squared, 3 to the 2 power is 9, and 3 to the 3 power is 27. So the answer's got to be somewhere between 2 and 3, probably a little closer to 3 because 20 is a little closer to 27 than it is to 9. But in order for us to solve that, we have to take a logarithm of both sides. And again, I like the ln myself, but the log also works just fine. You just can't mix and match them. And when I take an ln or a log of the left-hand side, what it allows me to do is take this x that's in a power and bring it in front. And so really this reads as x natural log of 3 equal to natural log of 20. Then I can divide both sides by the natural log of 3 to find what my answer is. And in this case, x equals the natural log of 20 divided by the natural log of 3. So let's bring up our calculator here. Put it over here, and we'll say first 20. Actually, we have to, in our case, we have the natural log first, and then we put in 20. We want to close the parenthesis before we do anything else. Then we want to hit the divided by symbol, and then we want to put in an ln again, and this time put in 3. Close parenthesis, getting good habits, and then hit enter, and we'll have the answer. We know it's somewhere between 2 and 3, and indeed our answer produces that. It's 2.727. I would prefer 3 decimal points if you're going to use a decimal, and that's fine. There is our 3 decimal points. So if we need to answer the question of a exponent, such as time, could be also n, although n is there twice. Usually they won't force us to do something like that. We can do that given what we've seen. All right, so let's take a look now at example 7 on page 403. DD has invested $8,500 in some old Star Wars memorabilia, which is currently increasing in value at 6.5% per year. If this increase continues at the same rate, in how many years will DD's investment double? All right, so remember we talked about this once before. It doesn't matter how much we start with. Doubling time, tripling time, quadrupling time, whatever it may be. The P is not that important, right? Whether it takes, how much time it takes to double from $1 to $2, or from $8,500 to $17,000, or from 1 million to 2 million, given the other parameters of the question, will all be the same. But let's go ahead and set up what we know here in this other part. Actually, let's minimize this piece first since we're done with this, just so that we can have more space to work on this other one. So I'll take this, take to the power of Microsoft Paint. We're going to make this a little bit smaller, have that as our guidepost up here. Let's stick it over here on this end so we have it. And then we'll proceed on. So put our brush back on. And let's put down what we know here in the middle so far. So we know that we're starting with $8,500. That's our P value. We know we're talking about doubling time. So technically the A is 17,000. Although again, I'll show you in just a few minutes, this is not that important when it comes to the P and A part here. All right, the interest rate they gave us was 6.5%. What we need that to be is 0.065 for us. And then the time, well, that's what we're trying to figure out. We don't know what the time is, so go ahead and put a question mark by that one. And then the n value, we might as well just put that right here. The n value is it's doubling per year. So basically it's compounding once per year. And we can still use our equation. Our equation doesn't break if n is 1. In fact, it makes it even easier to use if n is 1. All right, so let's set up with what we know. We know that the final amount is 17,000. We know the initial amount was 8,500. 1 is 1. The interest rate is 0.065. The number of compounds per year is 1. We're doing an annual compounding. The time is the unknown. And technically it's time times 1 here as well. Now we'll put that in there even though we know time times 1 or t times 1 is still just t. And that's okay. Just like 0.065 divided by 1 is still 0.065. And in fact, what we know so far then is that 17,000 is equal to 8,500, 1.065. I'm assuming we can all do that math, because 0.065 divided by 1 is 0.065, and 0.065 plus 1 is 1.065. And it's going to be to the power of t right here. All right, so the first thing we need to do is we need to divide both sides by 8,500. And this is the part where in the future it really doesn't matter about the 8,500 or whatever we're starting with or the end value, because 17,000 divided by 8,500 is 2. So right now we're at 1.065 to the power of t equals 2. How is that any different than when we did the previous example here where 3x was equal to 20? You know, our 3x is like our 1.065 to the t. Our 20 is like our 2. Yeah, they've swapped sides of the equal sign, but really it's the same exact thing. So to solve this, we're going to have to take the log or natural log of each of these parts. And so that's what we'll do. Let's go over here and we'll say we're going to have the natural log of 2 equal the natural log of 1.065 to the power of t. And by doing so, this t gets to come in front. So it reads as t times the natural log of 1.065 still equals the natural log of 2. And so then we're going to divide both sides here by the natural log of 1.065. And that's going to tell us how much time was involved in years to get this to double. All right, so we bring up our calculators again. Clear off this. We don't need this part here. But we're going to say ln. We're going to say 2. Don't forget to end that parenthesis. Kind of important. Then divided by. Then ln again. And this time 1.065. And parenthesis. Enter. And the answer is 11.007 years. So we'll remove our calculator and then we'll come down here and we'll say 11.007. And again, needs context, so we'll just put YRS right below it. So 11, just a little bit over 11 years for it would take for this Star Wars memorabilia to double in price. Is that good? Is that bad? Again, it's not neither. I mean, it really depends on what inflation is doing. I mean, yes, inflation's about 3% every year is roughly what inflation is. So it's about double of inflation. So yeah, this should be a significant amount of cash that goes forward. Now that's a lot of work. So let's see if we can come up with a kind of a cheater's equation that goes with this instead. If we're talking about X time, right? So let's say we're talking about doubling time, tripling time, whatever it may be. You know what? We need some workspace if we're going to make this work. So let's go ahead and make this just a little bit smaller. So what's a cheater's equation that we can come up with that we can use? All right, let's call it X time, as in doubling time, tripling time, whatever it may be. All right, so here's how we're going to do this. We're going to say that to get the time for it to double, triple, whatever, we're going to have an ln of the X, if you will, the X time. Okay, if it was doubling time, it's going to be 2. If it's tripling time, it's going to be 3, whatever it may be. And then we're going to divide it by the natural log of 1 plus r over n, and then any n that's needed as well. So this is how we're going to get there. So if we wanted to talk tripling time or quadrupling time or whatever it may be. So let's talk tripling time for a moment on this last problem. How much time would it take for us to triple in value? All right, so that means that time would equal the natural log of 3, because we're talking about tripling time, divided by the natural log of 1 plus, the interest rate was 0.065 again, divided by 1, and again, power of 1 here. All right, so we could totally do this in our calculators. All right, that's the fun part of this whole mess, is that it can be done that way. Certainly we can realize that once again that 0.065 divided by 1 is 0.065, and 1 is up here. And so really our denominator is the same denominator we used over here, which is 1.065. All right, so now let's use our calculator and put this in here and to get the answer. So let's bring our calculator up. Let's clear anything that may still be there. Looks like I'm empty on this one right now. Let's put it over here where we can see it. We're going to hit the ln button. Then we're going to hit 3. And we're going to close the parenthesis. Again, very important. Divided by. We're going to hit ln again. We're going to put in, if you wanted to, you could put in 1 plus the 0.065 divided by 1, if you wanted to. That would still work. Your calculator is smart enough to interpret that. And again, it's to the power of 1, so if you wanted to set it up that way too, we could. We could put everything in that we wrote down to get the answer we're trying to achieve, and then we could say enter, and we'll get the answer. In this case, it's going to take roughly about 17.5 years, but 17.445 years to make this one work. So 17 years, or just a little under 17.5 years for the value to triple in value. But this is our equation now, right? We want to use this equation here. We're talking about doubling or tripling time or whatever it may be. So it's a secret hidden equation that I've just now given you, that if you need doubling or tripling or quadrupling or 2.5 times, whatever it may be, this is it. Count yourself lucky that I like you.